Let's look at the following problem in projectile motion. A stuntman attempts to jump across a river on a motorcycle. The takeoff ramp was inclined at 55 degrees, so alpha is 55 degrees. The river is 50 meters wide, so that is the river. The bank on the other side is 20 meters lower than the top of the ramp. So this is the bank on the other side of the ramp. And as you can see, the bank is at a level which is 20 meters lower than the top of that ramp. The river itself is 110 meters below the ramp. So that is the depth. Find the speed u of the stuntman at the top of the ramp if he was to just made it to the edge of the far bank. So that speed, provided that he follows that trajectory and he lands there. So let's first set up the coordinate system. I'm going to take the x-axis to be like that and the y-axis to coincide with that wall. So that is the origin. Now let's set up the equations. While the stuntman in motion from this point to that point, he is under the influence of gravity. So while this is a two-dimensional motion, he's moving both in the direction of x-axis and also along the y-axis. The acceleration is purely vertically downward, namely along the direction of minus y-axis. There is no acceleration along the x-axis. So the acceleration along the x direction is 0, and the acceleration along the y direction is minus g, where g is 9.81 meter per second squared. These are constants, so kinematics apply. Let's write down kinematics equations along the x-axis. The x component of the velocity for the object, namely for the stuntman, is the same as just the x component of the takeoff velocity, namely the x component of u. And that is just u cosine alpha. Alpha is 55 degrees. So u cosine 55 degrees. The second equation describes the variation of the x-coordinate of the stuntman while he is moving. And that equation is half x component of the acceleration, t squared, plus uxt, which is the x component of the initial velocity, plus the original x coordinate. In this case, he's starting from there, so the x coordinate of that starting point is 0, so that is just 0. There is no acceleration along the x direction, so that term is 0 as well. So x is simply uxt, ux given by that expression. So that means x is u times t cosine 55 degrees. Now let's write down kinematics equations for the y direction. The y component of the velocity at any time t is given by the y component of the initial velocity plus the acceleration along the y direction times time t. From the diagram, we know that uy is u sine 55 degrees, and ay is just minus g, as we have described earlier. So that equation will simply become u sine 55 degrees minus gt. Again, we note this is the initial velocity, that is 55 degrees. So ux by trigonometry is u cosine alpha, and uy is u sine alpha, alpha being 55 degrees. Now let's write down the equation that describes the changing y-coordinate for this stuntman while he is in motion. That is given by half the acceleration along the y direction, t squared, plus uy t plus the initial y-coordinate of that stuntman. Ay is minus g, uy is u sine 55 degrees, and y naught This is the starting point of that stuntman. The y-coordinate of that point is 110 meters. So substituting these information in this equation, we get all that. Now we are ready to solve the problem. When the stuntman lands there, let's assume the time he takes is capital T seconds. And the coordinate of that landing point, the x-coordinate of that landing point, is 50 meters. So x is 50 when time is capital T. Let's substitute that information in this equation. And you'll get x equals to 50 and time is capital T. The y-coordinate of the landing point is 110 minus 20. That means this point right there, the y-coordinate of that point is 90. What that means is when time equals to capital T, y is 90 meters. So let's substitute that information in the second equation for y. You get y equals to 90 when t is capital T. So t squared here and u capital T there. So there are two unknowns, u and capital T, and there are two equations, and we can solve them simultaneously. Let's solve for capital T. From this equation, you see that u times capital T is quite simply 50 over cosine 55 degrees. Let's substitute u times capital T in here, and you can solve for t. If you do that using a g value of 9.81, you will find capital T to be 4.32 seconds. So that means the stuntman takes a time of 4.32 seconds to travel from here to the landing point. Having found capital T, again you can use this equation to determine the value of u. You see it is just 50 divided by t, which is 4.32 seconds, times cosine 55 degrees. Cosine 55 degrees, which will give you a value of 20.18 meter per second. So that is the speed of the stuntman at the top of the ramp, and that solves the problem. Thank you for watching.